Hi, so today we've got some rather interesting bits of kit to look at. These are digital X-ray flat panel sensors. These are used for sort of X-raying people in place of traditional film. So these are sort of a large sensing array with an internal scintillator. I believe they use tech very similar to TFT LCD panels to generate an array of light sensors over a large area, probably on glass, because obviously that's a cheaper substrate than silicon for things of this size. This largest one's about 430 by 370 millimeters, so these are sort of big sensors. I've got two of these Samsung ones and two different sizes of these Canon ones, which are very similar inside. Now I would quite like to at least get one of these working for use in my mailroom X-ray, because I think these would have a much higher resolution than the camera system that's in there at the moment. I believe the resolution on these is something of the order of 4 to 6 pixels per millimetre. These are very expensive originally. Even today we're talking sort of tens of thousands of pounds each. I suspect these might be damaged. Some of them had little shock sensors on there, and most of those had tripped, so maybe they've been dropped. So may well be that the actual panel's damaged. One of these also has liquid damage, so I think I'll probably do an extreme teardown on one and actually sort of go right into the panel. But haven't found that much information online. I did find a user manual for the Samsung ones, which had a few very small snippets of information, but nothing hugely useful. These all have Wi-Fi interfaces and internal batteries, but at least certainly the Samsung can be used in a wired configuration where it's powered by a cable, and also the data is downloaded from it via the cable. Now I have actually had all these apart, and I think for reverse engineering the Samsung one looks more promising. I'll go into that a little bit later, and reverse engineering is going to extend into another video. It may well be that someone out there's got some information, because it'll be useful just to know a bit more about the operating procedure. For example, do these need to be like paired up with a receiving system before they start X-raying, or can you just shoot an X-ray and then download it later, that sort of thing. It'd be quite useful to know just the details of the sequence of operation of these things, just to get an idea of how I might be able to get them to do something. The user interface on these ones looks pretty similar. We've got there's generally a button on the side, three LEDs, so you turn it on, it waits for a file to start up, then you then get a ready light. They all appear to be able to detect X-rays automatically, because of course this could be part of a system where the X-ray machine can tell the panel when to take the shot. But of course sometimes X-ray machines are expensive, so you may well want to use these to upgrade an existing X-ray facility that was using film, or some of the other types of detector, like the image transfer type detectors. So it may well be that you'd want to use this with a system where it can't have a direct interface to the X-ray generator. In that case, these sit in a mode where they can detect the X-ray either by running the panel at its full acquisition rate, or maybe using a slow scan or scanning part of the panel to detect when the X-rays are on, and then going to the full acquisition mode. And I think the X-rays are typically of the order of like a few hundred milliseconds up to a few seconds. Again, I don't know whether these would like do a single exposure or do multiple frames and then combine those in software afterwards. There might be some clues if we can get some waveforms out of them. So these are sort of fairly solid, and there's like a fairly solid sort of casting. So obviously these are going to be put underneath, you might actually have like a patient partly sitting on these, or there's some instructions in the manual about the exact amount of weight they can take, but they are sort of very robust, and they're pretty heavy. This is probably a sort of couple of kilos at least. Now on the back we've got the battery, sort of a fairly slimline battery. I think it's got tape on, so I actually split this battery apart just to figure out all the contacts and give it a bit of charge. They're sort of very slim lines. Obviously these have to fit in the place of a standard film X-ray cassette, so these are obviously designed to be the same dimensions as a standard film cassette. So the batteries are sort of very slim, so the whole thing is about sort of 15 millimeters thick or so. That's 11.1 volts, 2490 milliamp hours. So the idea is these can run for quite a while, get a good few hours of usage, and I suspect they normally live in a sort of charging cradle. So on the side we've got there's a Wi-Fi antenna behind there. We've got an infrared link. There's one button, so sort of press to switch it on, and there's also a connector here, which is, it looks like a fairly sort of delicate sort of connector for routine use. I'm surprised they use a really fine pitch. And this one has got some evidence of liquid damage, so maybe when it was being cleaned or disinfected, some liquids got into there, or maybe a patient had a slight accident when sitting on top of it. This panel, this is just a little plastic insert in the main metal panel with the Wi-Fi module underneath it, just to get a bit more signal out. So inside you can see sort of some similarities to a TFT LCD, so which is a very similar technology. We've got sort of a load of sort of tab-mounted drivers on one side, and there's also a connection here, which again will be the similar sort of drivers on that side. So one side will probably be putting out like a scanning waveform, and the other will be putting out analog data to be digitized to produce the image. So taking this metal strip off, there's actually some thermal transfer material on top of these chips. These are actually pretty large chips. That's maybe sort of 15 by 8 millimeters. Unless they're on the other side, I can't actually see any A/D conversions. So it could actually be that these are the A/D converters. It could be there's a multi-channel sort of multiplexer and A/D on these ones. But there might be some stuff on the other side of this board. We'll take a look at that. But there is quite a high pin count. Say all these tab chips bond onto the other side of this PCB, so there's clearly quite a lot of connections going onto this board. Second board, we've got a load of digital buffers here and lots of ultra low noise analog op amps and some power type stuff. So there's clearly some analog stuff going on here, because we've got these analog components. This, I'm guessing, is maybe power supply regulation. Again, the actual, because with X-rays, you want to use the minimum amount of X-ray you can. These are going to be like as sensitive as possible to get the absolute maximum sensitivity out of the sensor. Certainly the Samsung, the spec on that says it's a 14-bit image capture. I'd imagine this is going to be similar, somewhere between the 14 to 16-bit sort of range. And again, everything be maximised for absolutely minimum possible noise to get the maximum amount of image data out of it. Because just sort of cranking up the X-ray power is not really a good option, and certainly they'd want it to be equivalent to a film cassette in terms of sensitivity. And over here, this is clearly a power board. This connects to the battery. We've got some linear tech, DC-DC modules, tons of inductors. So this is clearly just doing all the power management stuff. And over here we've got the processor board. We've got a big lattice, ECP3, FPGA. There's a TMP A910 ARM9 processor, some just flash and RAM, bit of RAM on the FPGA. They're probably going to be using FPGA to do all the timing control for the panel, and maybe also some of the signal processing. We've got a flex cable here to the side PCB with the infrared sensors and buttons and LEDs. There are signs of liquid damage on all these boards. There's a sort of white residue on here. So we'll take the boards out and take a close look at that. Over here we've got some shielding, some foil there. I'd expect there to be some sort of foil shielding for some foil shielding, possibly partly for X-ray filtering, but also obviously for electromagnetic shielding, so that's probably just grounding that. And down here there's a Canon branded Wi-Fi module, Wi-Fi antenna next to it. And this little connector board just going to that multi-way connector. If we look at the larger panel, it's very similar. The boards aren't the same, but clearly they've got very similar components. Again, we've got the power board, processor board. Again, the same processor and FPGA, but it is actually a different PCB. I suspect these are probably just two different generations, so it may well be there's a smaller version of this that uses exactly the same boards, but these are probably slightly different generations. So it's probably more the difference from one generation to the next we're seeing, rather than just the difference between the sizes. And also we've just got some space there. So again, this is clearly designed to be usable with a smaller panel. You can clearly see how this would shrink down. And again, we've got this intermediate board, again with a bit of analog stuff there, and some op amps and the like here. And again, we've got this other board connecting to the panel, so very, very, very similar. One thing I did notice on both of these is that some of these op amps have got orange marks on them. I wonder if that indicates they've actually been selected for sort of minimum noise or something, or performance. But you can obviously see marks on programmable devices, but there are just some specific devices that have these marks on them. and they're op amps, which I can only assume it's some sort of maybe selection, perhaps a minimum offset or something like that. Okay, so there's actually pretty much nothing on the bottom side of any of these boards. Some just a few 0201 decouplers on the under the FPGA on that board. Nothing under any of the others. So this board's quite interesting. So I think this probably is the acquisition side of things, because the board down here has got pretty much nothing on it and very few connections. So I'm sure that's just scanning, doing a row select type of thing. So it looks like all these devices here are on a sort of common bus. You can see sort of common parallel bus running up this board. Some pretty huge chips on here. These are about 18 by 8 millimeters, so these will clearly be quite expensive. Incidentally, I found some specs on this. It's 2192 by 2800 pixels, so it's about just over 6 megapixels, and the pitch is 125 microns. So just a quick close-up look at these PCBs. This is the power board, some Linear Tech DC-to-DC modules. These are quite nice, sort of very high power density, fully integrated DC-to-DC modules. Obviously lots of other converters, tons of inductors. Actually, it looks like I'm guessing some of those inductors will probably just be series filtering rather than part of the switching regulator, because there don't seem to be that many regulator chips there. Polyfuse there. Instead, there's a manufacturing date of 2012 on the back of this unit. The date on the other larger one was a bit too smudged, but there's what looked like a 2012 date code on the chips inside. Obviously signs of water damage, or liquid damage on there. And this interface board, so we've got these bus buffers. So there's about 64 bits on there, so it's maybe a number of parallel buses. Quite interesting, we've got all these like super low noise op amps, but we've got no HD conversion, so maybe these are just providing various voltage rails or something. It just seems interesting that there's all this analog stuff here, but no obvious HD conversion, which I presume is on the those tab bonded chips on the edge. Also, a lot of these film capacitors, that'll be for low noise, because ceramic capacitors can be slightly microphonic, so the film capacitors give sort of the best performance in low level applications. There's a few what look like maybe some build options, just sort of bunch of 0 ohm resistors and some test points. Maybe that's for selecting different panel types. It's ref, so maybe ref means voltage references perhaps. And the processor board, this has got LFE370A FPGA. It's not hugely big, it's only got 67,000 logic cells, but it's got a lot of memory. It's got about 4 megabits of RAM on board. A couple of RAM chips, ARM9 processor, RS232 interface next to a connector. I think we need to explore that. And the rest of this is just power. There's an Ethernet transfer. There's an Ethernet pulse transformer here, so that goes to the connector off to that multi-pin connector on the side. So that's the external hardware Ethernet interface. Some power stuff. Ethernet interface. A little lattice CPLD there, and some serial flash. There's a connector next to that serial flash. That's possibly a programming connector for that. That's probably the FPGA configuration data, I would imagine. Again, there's quite a lot of signs of moisture damage. Some sort of rust on that crystal cap. Tiny. I originally thought the back of this board was blank. I just run my finger over it and just about feel these little capacitors there. On this board here, there's actually very little. There's just really nothing really but passives on here. So clearly, these are probably doing sort of the front end and analog to digital conversion. I would think there just doesn't seem to be enough on this sideboard for it to have anything to do with the conversion, unless the sort of conversion I'd expect that this to be converting a number of channels either in parallel or semi-parallel, so that it selects one line at a time, and then multiple channels get converted to get a reasonable update speed. But there's really just purely passives on this this PCB. This little connector board, which is taking the brunt of the liquid damage, just looking at what's coming into it. Looking at the connector that goes to the Ethernet, there's 2 lines from the Ethernet transformers. That'll be sort of 10 meg Ethernet because it's only using 2 pairs. But there's also an RS422 driver that's setting 3 pairs of RS422 to that connector as well. So wonder what that might be. A switch on there saying ATDI and TDI, whatever that means. And this side connector's got the LEDs, as well as this IRDA transceiver. And I can think of a few reasons why you might have this. Obviously one situation is that you might have several of these in a facility, and especially if you're working wireless, you might actually want a way to know which of these is which, because obviously you don't want to get x-ray data for the wrong patient. So perhaps when this sits in its charging cradle, it exchanges some information just to identify it, or it may be just some other sort of configuration type interface that's used when you're not using the hardware Ethernet connection. So again, I'd be quite interested to know if anyone knows anything about just how these things are used. It'd be interesting to know whether that interface is used and just what the overall procedure is for the sequence of operations for using these things. And of course, if anyone's got the software, that would be super good. So I decapped one of these driver chips. I haven't got any chemicals to do it. I just used a hot air and scraping. So the hot air's just softened it. It took quite a long time, so there's quite a lot of damage to this, but you can get a rough idea. You can see there's most of the chip is sort of some per channel circuitry, and then there's some other stuff on this edge, which is the edge near the PCB, which interfaces to the rest of the system. There's a little bit down here, there's very little text, there's no sign of any manufacturer information or names or anything. There's a little bit of text here, which I'll show in detail in a sec. And then just this right side, they will go into this sort of, they fan into here, which may be some sort of decoder or selector or something, but say there's most of the chip is this per channel stuff, which is presumably some sort of ASD conversion. So there's this little bit of text saying TG1, and then various bits of text, 0.6 micron, 0.5 micron, etc. Those can't be the dimensions between those pads. They're too big for that. But can't really tell a great deal from that. Right, so I've managed to prise this out of its frame. The frame's just got a sort of plastic, it's like a sort of soft rubbery material here, and some sort of non-metallic. I'm not really sure what this material is. It's obviously, it needs to be X-ray transparent. Might even be graphite actually. It sort of seems to sort of scratch quite easily, and yeah, it's pretty conductive. So yes, I'd imagine that front panel is probably graphite. And that's sitting in this sort of strong cast frame. This is a very, very rigid frame. You've got this aluminium foil, so the scintillator material is going to be inside here. The aluminium is probably an X-ray filter to manipulate the wavelengths of X-rays it's sensitive to. And it looks like we've got a glass panel about 1 millimetre thick, and then a fairly rigid plate, which is what everything's mounted into. Some tape around the side, and this liquid damage all over the place, so I'm not too worried about tearing this one to pieces. So you can see that was that shielding section that we saw earlier on, so that's coming from this front. So I'm guessing this is probably a sort of laminated sandwich of sort of aluminiums, probably sort of laminated together with so that would be sort of either deposited directly on the face of the glass, or there might be some transparent things. Could maybe be a separate laminated assembly with a transparent back to let the light through to the sensor. So it looks like this back is also graphite. I wonder if maybe that's to for absorption of the X-rays, to avoid the sort of scattering or reflections. Obviously, if the X-rays coming in, you don't really want it to reflect and blur the image. So maybe that's just there for absorption. It looks like it is some sort of sandwich though. There's some silver in between the layers here, so this looks like a sort of sandwich of at least 3 different materials behind the actual glass. So incidentally, according to the data, this is a cesium iodide scintillator. which as far as I can tell isn't ridiculously toxic. It's probably a little bit hard to sort of make out the layers, but basically we've got glass substrate and the silicon is actually deposited onto that. According to the data, it says this is an amorphous silicon sensor. Then there's like a thin layer of lacquer on top of it, and then we've actually got the scintillator material, which I'd guess is maybe about 0.5 millimeter thick, and then this aluminium foil coating on the top. I think this scintillator material might be sort of fairly atmospheric, moisture and moisture sensitive, and so this sort of foil, it's like, there's like a sort of aluminium foil plus sort of plastic sheet, so this might be partly about moisture sealing. And so I'll scrape this lacquer off. You can just, it may not come over the camera, but you can just see sort of the colour of this little silicon film on top of that. And it looks like the glass is pretty well bonded to this graphite sheet, so I don't think there's any serious chance of getting that out. I don't think there's anything interesting to see really. I'll ground this edge down a bit. It looks like this is made of carbon fibres. You can see the alternate layers and the fibre strands, but there is also a metal mesh in the middle of it. I'd imagine this is probably for electrical shielding rather than X-ray shielding. So for X-ray shielding you'd want it to be continuous rather than a mesh like that, I would have thought. But this is an extremely stiff rear panel, so obviously that's for mechanical strength. Looking at the actual panel under the microscope, this is the section at the corner where the two drivers meet, and you can see there's like some sort of vertical bar along the left hand side. Wonder if maybe those devices there are perhaps ESD protection diodes or something, or pull-ups or something. Seems to be one common connecting each of those row connections, and you can also see the layers that have been sort of gradually peeled off. There's sort of an upper lacquer layer, and there's at least two active layers. The ones that appear sort of greeny blue seem to be the actual sensing pixels. And if you look here, you can actually see sort of on the left hand side you've got these sort of presumably the actual image sensing part on the left, and then on the right a switching device underneath it. So obviously you want a fairly large fill factor for the pixels to get the maximum sensitivity. And then looks like the switching device is underneath it. You can see on the left hand side you've got this look like a vertical column connecting the top side of those pixels, a fairly small gap between them, and then a link down to this transistor underneath. So this will presumably be switching it based on the row enables. So it switches one row of sensors onto the analog sensing lines one at a time. And the drivers on these, pretty sure these are standard, fairly standard TFT row drivers. There is actually a part number on here, S1D 17928, and that gets a couple of hits on Google as an LCD driver chip, so these are probably pretty much standard. So there's pretty much nothing on this board, so I'm sure this is probably just one great big shift register that shifts a bit through just to select one row at a time, while the these chips along the top actually read the analog data out for that row. So I've started a bit of reverse engineering effort on this Canon unit. Had a poke around. It's fairly obviously a small connector. I thought it was probably a serial port. Poked around, and yes, turned out we got a load of text on startup. Also connected the Ethernet. I traced the pins from this micro Ethernet interface through the pulse transformer to identify the Ethernet connections, which I sort of connected directly to. So this is what we see at startup, Dryos by Canon, which appears to be a Canon proprietary operating system. They also use some in their camera products, plus sort of various hardware stuff that you'd normally expect to see in a boot up. Some stuff about calibration data, something about accelerometer. There's probably an accelerometer for checking position and which way around it is. IR, when these messages are showing, there are some infrared flashes from that infrared interface. I'm guessing it's probably trying to communicate with its docking unit. And the network does seem to connect, and the link light comes on the side. But also we actually have a prompt. So help. We do have a small sort of range of commands there. I've only had a very sort of brief play with these, but there's nothing hugely interesting. That suggests that we've got UDP and some TCP ports, so presumably it's listening for some communications from the workstation to control it and get the images back. Counter thing, which implies that it's taken a bit over 3,000 shots. Interesting, it's also showing shot count, so that is probably logging if it's been dropped or anything. So the Samsung one had some little glass shock detector things. This one looks like it's using the accelerometer, and when it's turned on it's pulling about 40 odd milliamps, even when it's sort of supposedly switched off, so I think it's probably running that continuously. So I've had a bit of a play around with this, I say, because it's not a standard operating system. It's there might be some stuff in there, but it could take quite a long time to figure out what's going on. Now there's a print log command that would just spewed out tons and tons of data. It just kept on and on. But there's what looks like some actual operational stuff in here. We've got event go to ready, expose ready, approve, expose request, and then some stuff here that looks like it's to do with downloading, sort of frame leader, payload, etc. So that might help, but I think the problem with this is, because it's probably not a very well documented operating system, it could be quite difficult, and so we'll see on the Samsung that actually looks quite a lot more promising for a few reasons. But obviously there's plenty of stuff you could play around with this and might actually get some interesting bits of info, but the other one I think looks a bit more interesting for the moment. Okay, this is the Samsung panel. Slightly bigger battery, but again still sort of a nice slim thing. It's got a nice little LED battery level indicator, and on the side we've got something that looks a bit more like a sort of sensible docking connector with a couple of magnets on the side, and I found some Samsung user guide, and it shows like a lead that just clips onto here. That's got power and Ethernet on there, simple interface button, 3 LEDs. Now this one's a bit trickier to get apart if you want to get it back together again, because the back panel is covered by this sort of sticky thing which you've basically got to take off. If you take this label off, there is actually a section here that can come off without taking this main sticky off, but you still have to destroy this label, and that just allows some access here, which if I take the back off it'd be easy to see what that access is. This back panel is very lightweight metal, it's maybe magnesium or something, it's pretty light. Yep, so the things that are accessible through that back panel are the Wi-Fi module, because there may be different modules for different countries. There's an SD card socket, a couple of buttons and a connector. That looks quite interesting from the point of view of connecting stuff to it, and some sort of quite noticeable differences in the architecture of this. And obviously we've still got sort of the battery, we've still got a power board, everything else is on this sort of main board here. We've got A to D converters on this board. We've still got some moderately big chips along the top, not quite as big as on the Canon, and some much smaller chips down the side, which again may or may not be standard TFT chips. The other notable difference is there's crap loads of capacitors on here. So in this top row there's a big load of ceramic and tantalum caps, and there's a huge bank of tantalums here. Each of these is 10 microfarads, and looking at the size of those, they're like D size, so 10 microfarad D size means they're probably a fairly moderately high voltage, maybe sort of 35 volts, something like that. purely because of just the physical size. And there's massive great ceramics as well, so this is clearly a somewhat different architecture to the Canon one. Obviously Samsung make LCD panels, so they're probably using the same tech in there for these X-ray panels. And there's some labelling on here. It says gate IC and ROIC, which is obviously readout IC. Now fortunately these chips on this one don't have all the epoxy over them, so you can actually just about see some structure on there. Can't really get these under the microscope, obviously I don't want to destroy this panel, at least not yet. But you can see there seems to be like a fairly simple structure, and there's almost actually looks like there's either quite a lot of space, or maybe that's just a gap on one of the metallization layers and the stuff under there. But they it seems to be sort of relatively simple, uniform blocks. There's a sort of set of blocks on the left hand side where the panel connects, and then the right hand side which is the connection to the board. So, but the fact that we've got HD converters on the main board suggests this is probably just some sort of analog multiplexer type of thing, so it can just scan and produce output one or several of the analog outputs and be fed into the HD converters. Again, these the road drivers, again it's hard to tell, and these could be standard TFT drivers, or they could be something custom, but obviously they're going to be doing a sort of pretty more simple task. The die size is quite noticeably smaller. It's a bit hard to see that. So that's the die on the road driver, whereas that's the column one. Power board is pretty much what you'd expect, just tons of switching converters and regulators and stuff. There's an Atmega 128 there, which I'm guessing is probably mostly to do with power management, charge control. If there's an accelerometer on this, then it may well be connected to this. And these panels had 4 of these shock sensors around the outside of the frame, most of which have gone red. I think the way these work, these have got a thin tube of red ink on the inside with a weight on it, so that if it experiences a shock, the tube snaps, and then that distributes the ink. So I think this is an untripped one, and this is a tripped one. So we can probably, so if we flick that, we can now see that's gone red, to show that we've given it a shock. And obviously, sort of being a glass sensor panel, the reasoning behind that is just a shock could potentially crack that glass sensor. So that's probably a sort of a warranty type thing. So along here we've got 6 analog devices, AD9240. These are 14-bit 10 megasample per second HD converters. There's a few sort of op-amps here, not a huge amount, and each pair of these goes into a MaxV 5M5770Z CPLD. And by looking at the tracking, it's fairly obvious. We've got parallel data going into these CPLDs, and then we can see these diff pairs coming out of here. So those are turning it into a high-speed serial stream, and that then gets fed into this Spartan 6LX45 FPGA. That's going to be handling just the data formatting, maybe some processing. There's a RAM chip next to that as well, so that could be doing things like dead pixel compensation, that sort of stuff. Maybe accumulating the results from multiple frames. And the main processor here, this is a TI AM3358 Scintillator series processor. The manufacturing date on this is 2014, so this is a relatively recent one. The date on the other ones look like 2012, so neither of these are particularly old. So presumably they've gone out of service because there was a problem with them, or they got damaged or something. And not a huge amount else on here. So we've got an Ethernet transceiver, the magnetics, Ethernet magnetics here, some power management stuff, wireless module. This is just the USB cable going up to the wireless module. For some reason they used a great big long cable and folded it rather than using a short cable there for some reason. It's just an off-the-shelf cable they were using. And so there's not much on these sideboards. There's clearly some power stuff. There's some bunch of polyfuses, just tons and tons of these tantalum and ceramic caps. These connectors, these look like sort of ordinary single wire connectors, but actually they're not. They're actually micro coax connectors. So you can see we've got a big ground plane on one side and all the contacts on the other. This is a 0.4mm pitch, so each one of these is actually a separate piece of coax. Obviously that gives you good signal integrity, but but no doubt these are somewhat expensive and rather hard to get hold of as well. There's an unused one of these connectors over here. Now my first thought was, oh, that's just for like maybe a bigger panel that's got another connector, because we've got this one going up to the road driver board. But then I just started poking around looking for serial stuff, and the first thing I spotted was an RS-232 driver on the power management board. I really don't know why people still use RS-232 drivers. I mean, is RS-232 really still a thing? Surely everyone uses TTL these days. So it makes it easy to spot. That comes out on this header here. This header here is, I thought it was going to be the ISP for the ARM, but it isn't. Sorry, for the AVR, it isn't. It seems to have TTL level serial and one or two other signals, processor reset and a few other oddments on there. But the interesting thing was that the RS-232 on here also goes onto this connector, which is clearly the power in connector. And there's a couple of tracks on this that actually go round here and then all the way back up to the main PCB. And I just traced through those pins, and they do actually come out on here. So this is clearly, it's got at least one serial port. There's another couple of lines which I believe are probably serial on this side connector, and that also comes in here and then also goes up to this connector. So I'm pretty certain this is going to be a debug connector. Also the fact that there's no other sort of obvious debug connectors on here. So obviously it's good that we found where to look for a serial connector. The problem is it's this weird bloody stupid connector. Now if it was just the serial and nothing else, then I probably would have just tacked a couple of wires on here. So this is a 0.4mm pitch, but there's clearly other stuff going on here. There's some what looks like possibly a set of 4 or 5 diff pairs going on there. There's a set of 4 connectors there, so there could well be some other interesting stuff going on this connector. Now, because obviously I've got 2 of these panels, if these weren't micro coax, I'd have simply just chopped one of these and just broken this out to a bit of perf board, because obviously I could potentially, if I wanted to, then resolder it back and actually get this back. But because this is micro coax, I think that would actually be really, really difficult to do. Fortunately, the entry, this is like a solid entry, and there's like springy contacts within the connector, so that all we need really is a solid piece. This is about 0.4mm thick. So I was thinking, okay, a bit of 0.4mm pitch PCB would probably do the trick. Now to make that plug, probably the easiest way would have been just to do a PCB on maybe standard 1.6 or 0.8 and just file it down to the thickness. But I was digging around in my drawer of random PCB meter and I actually found some flex photoresist. I don't actually remember where this came from. I'm sure I probably bought this years ago just because it might come in useful. I think I've used it occasionally, but it's like photoresist flex, so that literally took about half an hour to knock up some of these breakouts. I did 4 in different orientations just to pick the one that came out best, because say 0.4mm is getting onto the limits of what's doable on a sort of home etch with a laser print. Actually, I think the laser print is actually about one of the limiting factors on this. It's only a 600 dpi. Laser, but so it come out fairly reasonably. It plugs in quite nicely. I've stuck it down to some 0.2mm board just to get the rigidity, and just padded it out to get the right thickness, and that works out quite nicely. That's just tacked onto a board. I just soldered that to the ground plane just to keep it stable, and solder some pins on so I can just plug onto any of those connectors quite easily. I also traced out the pinouts for the Ethernet, so I went from this, although this is it's a sort of QFN type package, I sort of figured, okay, these pins are probably going to be in roughly the same order, and I just used the meters to trace out between here and the input of this pulse transformer, and then just soldered some wires on the other side to get the Ethernet connection. Okay, so plugging into that serial port on the power management board, we get a little menu. So this is going to be running out of the 80 Mega 128 type help. We get a little bit of help. So it looks like this is just setting and getting sort of various parameters. So we're probably not going to be able to do much with this. So say verb object token, verb is get set. So if we do get help. Okay, so we can do get system. Language English. Yeah, so this is just some fairly simple parameters for the power management. So you get versions and stuff. There's some, looks like some stuff to do with power management. You've got scale and offset, presumably for an AC converter, over voltage protection, over current protection. So adjust, there's some adjustments in there. Yeah, so 6 volts, 15 volts, 30 volts. That might explain those big tantalums. So these are just the calibration factors for probably presumably the measurements, battery voltage, etc. Yeah, so this doesn't look particularly interesting, so I think we need to take a look at what else we've got on that dense connector. So I did find a user manual for this online, which wasn't that useful, but it did have a whole load of GPL stuff in there, which told me it's going to be running Linux. And so we found this other serial port from the main chip, which has got all the usual Linux, however you want to say it, boot up stuff. Loading file systems, uncompressing cores. Interesting, it's got CAN bus on there. Maybe that's just part of the standard chip. Can't imagine what they'd be using that for. Network stuff, mounting file systems and stuff, check battery level, blah de blah de blah. Like the more system specific stuff here. We've got proprietary X-ray FPGA initialization. This world regulatory domain thing, this will be to do with the Wi-Fi, because different countries there are different channel allocations and powers and so on, so that's what that's going to be about. So stuff to do with FPGA, ROIC, that'll be the readout IC, so this looks like it's maybe configuring or doing something with the various readout chips connected to the FPGA. And this looks rather interesting. Press enter to activate console. Oh look, we appear to have a root console. Now I don't know a lot about Linux, but I know this is going to be somewhat useful. Okay, having done a bit of reading up on Linux startup stuff, this file in /etc/init.d looks like a sort of plausible startup thing, quite nicely commented. A few interesting things here, mounting file systems. I've not yet tried plugging an SD card into that socket, but I'll be my guess is that SD card socket is going to be for firmware update, so there's probably something in here about, updating the firmware if it sees the files on that card. Some stuff about the GPIOs. These actually control the LEDs, and I've actually played around with these. You can actually, I've managed to turn the LEDs on and off with this simple GPIO commands. Yeah, for example, these ones here, these GPIO out commands, you can turn the various LEDs on and off using those commands. Essentially, it's checking battery levels. Looking at the documentation, it looks like the system has two modes, either battery powered via wireless or via the physical Ethernet powered by an external cable. So I think it maybe looks to see where the power is coming from to decide what interface to use. Now this stuff, secure data and X data, that's actually a fairly simple file that seems to be mostly configuration data. I'll show what's in that in a second. So for example, wireless reading battery level. So this S cable is probably determining whether it's running in cable or wireless mode. mentioning here also reading battery level, and if it's below 3, kill upgrade process, so it's clearly presumably not allowing it to try doing a firmware update if the battery's too low. So it's running C1 upgrade, so that's probably a thing to check whether it wants to try doing an update. Yeah, there's a awful lot of stuff in here. And that X data folder has just got this file called security data, system version information, FPGA version information. Yeah, nothing particularly obviously security related in there, just some configuration type stuff. So there's lots of application related stuff in here. This is going to take quite a while to go through, so I'm just going to have a very quick whiz through it. Look at what processors are running. Again, I've no idea which of these are standard Linux ones and which ones are the application specific, but I'm guessing here we've got stuff C1 upgrade, which we've seen, X system, DR power off. Okay, so doing a quick Google around to get half a clue as to, I think what I probably want to try and do is mount the micro SD card and then just copy everything off of the main internal flash onto it to make it easier to look, so if it make out. So I've done fdisk L, and that seems to have recognised the, I've put a blank FAT32 card in there, so it seems to have found that, recognised the partition format. These are the devices that it's mounted by default. It seems to think that dev/MOSC block 0 is a thing. Oh, maybe that's what we need, the P1. Okay, so according to the internet, I need to do make a place to put it to, then mount 0P, I presume that's partition 1 /ONT/SD. Ah, we appear to have mounted our SD card, which is, and that's the file that was on it, so cats. Yeah, okay, so we now have a file system, so what we should presumably be able to do now is copy stuff onto it for more easy examination. Now just power this other unit up, and looks like there's got some corrupted NAND flash. It's throwing all sorts of bad block errors and not actually booting, so that might explain why this one this one got retired. I would have thought this would be fixable via sort of proper update using the SD card, but it seems to be sort of sitting into going into various boot loops and throwing all sorts of errors. Now the reason I'm firing this other one up is that I think I accidentally deleted a couple of files off of the first one. Okay, I think I might have screwed up on that unit that was working. I thought I was deleting some files off the SD card, but I think I actually deleted some of the application files off the main thing, which is a bit unfortunate. It looks like there might be some backup data on the, if you go into the U-boot menu, it looks like there may be some backup partitions that might be worth experimenting with, but I've not really had, I don't have time to look at that at the moment, so I'm going to leave this for the moment. So if anyone's got any information on these, then please get in touch. I realised I was probably going to have to, because of those faults on that other flash, I realised I was probably never going to have both of these working, so I decided to chop one of these connectors to make a more robust serial port connector. Initially, this micro coax is pretty crazy stuff. So this is that centre core. The insulation on that centre core is about 0.1 millimeter. So this is just ridiculously small coax. But yeah, so I might take another look at that Canon one, but say I'd be particularly grateful for even just something simple like what the normal operating procedure is, just to get an idea of what it's expecting to see. And so I'll still be quite like to be able to get at least one of these working, so it'd be quite handy to have in the Mailroom X-ray, but so I've got some other stuff to be getting on with, so I'll leave that for the moment.